So again, just make sure you understand where the negative sign is. Here, it was not in the parentheses. There was no parentheses originally. So now, let's see if we can do a few more of these. -3 to the 4th power, the negative sign is in parentheses. So this is equal to -3 times -3. We do it 4 total times here. Like that. That turns out positive because these two negatives will cancel each other out and become positive. These two negatives will cancel each other out and become positive. And overall, the number's positive. And then if you happen to know it, 3 times 3 times 3 times 3 will turn out to be 81. So this one will be positive 81. Now let's find something good. A nice, good order of operations that's getting there. We're almost there. Something like that. Absolute value. Let's work this one. So this one wants us to simplify your life, as it has always said. So we're going to remember our order of operations. What does the P stand for? Parentheses. E, exponent. M, multiplication, multiply. D, divide. Now here's the trick. Here's where it's really split up. Parentheses is its own step. Exponents is its own step. Multiply, divide, you do this from left to right, and you treat them like they're the same operation. So multiply and divide are considered their own step and do them from left to right in order. A, addition, or yeah, add is a better term for it. Subtract is S. Study your order of operations well and you will be wise. I almost did a Yoda voice. Yoda's that guy from, what is it, Star Trek or Star Search? Did anyone ever watch Star Search in the 90s? No, nobody did. I didn't even do that. No, he's from Star Wars. He first showed up in Empire Strikes Back. But Yoda voices are just kind of, they get old after a while, and I'm not going to do that. I'm not going to subject you to something like that. So let's see what's going on here. We want to do this one. We want to simplify, get all the math done. We're going to do what's inside parentheses first, because according to order of operations, that's what gets first dibs. What is 4 minus 6? -2. So this becomes 6 times, in parentheses, -2 raised to the 3rd power minus 2, open parentheses. Now we do 2 minus 4, which is what? Also -2. Also being cubed. So now we've taken care of parentheses in the sense that anything that was inside of parentheses has now been solved. So we're done with the parentheses stage. We still see some on the board. They're just there as an incident now, but there's no more operations inside of them to do. What would our next step be? Exponents. So we got to cube the -2, and they happen to show up twice here. So -2 cubed, the -2 is in parentheses. -2 cubed, that's going to be -2 times -2 times -2. Is that going to turn out to be a positive number or a negative number? Negative. And what will it be? Perfect. -8. So we've done the E stage. So it's going to be 6 times -8 minus 2 times also -8. What's next there, pilgrims? Make this a little smaller so we have more white space. There we go. Multiplication, exactly. Now we would do multiplication or division from left to right. There's no division here. Not even Tom Clancy's the division. So all we have to do is multiplication. What is 6 times -8 going to be? Going to be -48. Minus 2, well, no, not minus 2, sorry. Now we're going to do 2 times negative 8. What will that give you? So it'll be negative 48 minus negative 16, which actually becomes, exactly, that becomes plus 16. And you will be correct. It'll be negative 32. If you're unsure, just realize negative 48 is larger in absolute value, and it's negative, than the 16 is. So we know the answer will be negative, and then we can secretly kind of do 48 minus 16, which correct will be 32. So it ends up being negative 32. Do y'all want me to work another order of operations problem, or do you want me to move on to a different concept? Move on, move on, move on. Let's do that. So now we're looking at some algebraic expressions. Some of these may just involve us combining like terms. They like each other. Ooh, 5x and 8x. Did you see them talking in the hall? They must like each other. And when they like each other, they can combine into one single term. The reason that they're like terms is because they have the same variable structure. They both just have a single x. They may have different numbers in front of the variables. That's fine. That's the coefficient. But the variable itself is the same in both cases. Or if they were both just constants with no variable attached, they'd be like terms. What if I did that? What if I squared the x? Are these like terms anymore? No, they don't like each other. So they have to have the same variable structure. Once they do, you just add their coefficients. So what is 5x plus 8x going to be? 13x is exactly right. Imagine, and I know this is a corny example, but if you have 5 apples, I add 8 apples, now I have 13 of them together. The x is like the apple. It is what is the common category between these two expressions. And then I'm just doing 5 of them plus 8 of them. Yeah. So that's interesting. She asked, once I remember when I just put the squared on the x like that, could I distribute the squared and then add them together? No, because according to order of operations, the squared is happening only to the x at the moment. And we don't know what x is. So the best we can call it is x squared, and there's nothing more we can do with it. So this right here is as simple as it gets. There's no more simplification we can do. Yeah, they might get cute. Like if they wanted to do 5 squared x, I don't think you'll see that. That's rare. It's this case, the squared is happening to the 5. Thus, we can actually do it. We can compute it because we know what 5 is, and that'll end up being 25x plus 8x. So I guess it's possible. I wouldn't bank on it. It's just, yeah. Don't get me wrong. They like to trip you up. They like to give you, some trick questions and all that. But that's just not one you see very commonly. So let's continue on. Let's see if we can find a good one. Let's see if we can find a nice, juicy one. Yeah, we can try this one. So what we're doing is we're simplifying. We're going to combine any like terms, and then there's nothing left to do. We don't have to solve it. There's no equation to solve. We're just straight up combining of like terms. So the only like terms I see, the 3x and the 5x. You can rearrange the terms thanks to the commutative property, if you remember, of addition. I can put the 3x and the 5x together. I can put the plus 5 and the minus 3 together. I can put them right next to each other. You don't have to. If you can see where it's going to go, you can just jump straight in and do the combining of like terms right away. But in this particular case, it makes more sense to just combine them or put them near each other to help illustrate what's going on. 3x and 5x, are those like terms? Bet your bottom dollar. And what will they become? 8x. There you go. Plus 5 minus 3, are those like terms? Yeah, they don't have a variable attached to them. Thus, they're just numbers. You can add them up straight up. 5 minus 3 is 2. Muy bien, and that's all there is to do. Once you have 8x plus 2, you type that in that box, get out of here. You're done. Any questions on that one? And if you have any questions in the Zoom sphere, always feel free to ask questions. Interact with me. Let's do that one. Very good. I like that one. Hey, we should do the nastiest ones together, shouldn't we? Under my watchful gaze. So we want to simplify things, but everything's not on the same playing field right now. Everything's not on the same playing field. This business is in parentheses with a 4 in front. This business is in parentheses with a 2 in front. As a result, yeah, I see that this is an A and this is an A, but they're not the same at the moment. We need to get rid of those parentheses. We need to rid ourselves of parentheses. So we need to, I just heard the word distribute. We need to distribute this. We need to take this 4 and distribute it, and that'll help us drop parentheses. We distribute this 2. And then maybe everything will be on the same playing field, and we can talk about combining like terms. So this 4 will distribute. What will this become? Perfect. Does everyone see why? Because you're doing 4 times 2a. The a and the 4 don't intermingle, just the 4 and the 2. So 4 times 2 is 8, and you still have a sitting there. 4 times 5 is 20, and then there's still just a b sitting there. So now what does that second set of parentheses simplify to? 4, not a, but 4b, yep. And now everything's on the same playing field. We are now able to completely drop the parentheses. Now I'm not even going to rearrange the terms. We have 8a plus 8a. What will that give you? 16a. 20b plus 4b. What will that give you? 24b. And now that's as good as it gets. Those are not like terms, the a and the b. They're 2 separate terms. And that is done. That is in the books, my friends. Okay, so it's kind of hard to see because I couldn't fully zoom in. Here's the equation we want to graph. 8x minus 2y equals -8. First of all, you can tell that's going to be linear. A, because we haven't talked about graphing things that aren't lines. That's just not something that's come up in this course, and it does not at all, actually. So good job. How many of you are taking college algebra at some point? Are you taking college algebra? You will revisit this stuff for sure, and then add a lot to it. You'll dump a lot more onto it. This is a linear equation in standard form, we called it, or general form is one of the terms we used for it. It's not in the form we normally like, which is the y equals mx plus b form. So whenever you have it written in the standard form, normally you want to graph by intercepts. What you want to do, you want to get the x-intercept. You also want to get that beautiful y-intercept. Y-intercept. The x-intercept is going to be where the line crosses the x-axis. If you're a point on the x-axis, what is your y value always going to be? 0. You have no upwards or downwards motion. You're on the x-axis itself. Thus, you're going to plug a 0 in for y. You're going to leave x alone. You're going to have 8x. The y is going to be gone. You basically delete it totally from the problem. And we just solve this thing for x real quick. Divide both sides by 8. Oops. You're going to get x equals -1. But remember, it's supposed to be a coordinate. It's the point -1, 0. The x value is -1. The y value is 0 by definition. Y-intercept, get out of here. Delete the x now, because the y-intercept is where this thing is going to cross the y-axis. And anywhere it crosses the y-axis, you've got no left-right motion. You're in the middle. So your x value is always going to be 0 if you're on the y-axis. So we put a 0 in for x, which means it's just going to go away entirely. And you're going to get -2y equals -8. How do I solve that thing for y? Perfect, yeah. Divide both sides by -2. You're going to end up with what? Y equals, what's -8 divided by -2? +4, exactly. The negatives cancel out, basically. 8 divided by 2 is 4. Now remember, that's not, we write it as a coordinate, as a point. And that point's going to be 0, 4. 0 is your x value. And now we're ready to graph this guy, -1, 0. So I'm going to grab the line tool. There is the point -1, 0. 0, 4 is this point here. Bada bing, bada boom, you got that thing graphed. And you're right to be skeptical. There's -1, 0. Excuse me. So let's reiterate. Hard to zoom in on this thing, but basically -1, 0 is right here. I accidentally graphed 1, 0. -1, 0, and then 0, 4 on the y-axis. Connect the dots and you have a line. Yes? No, yeah. So the only thing we have to do with this one is graph it. And we know a line, think about if you wake up in the middle of the night and you need to go get a drink of water, the best path to take is a straight line. Now you can't always do that. But what we do know is that if you have 2 points, you have a completely determined line. So what we're doing with the intercepts is we're just trying to find 2 points that exist on that line. And it's an easy process because for either case, you get to plug a 0 in somewhere and get rid of one of your variables. So yeah, the -8 is, we're done. We've graphed it. We don't have anything more to do with this. Now, if we had it in y equals mx plus b form, we can immediately read the y-intercept off of that equation. And then from using the rise over run interpretation of slope, we can get a second point that way. But once you get 2 points, you have the whole shebang with the line. And that's good geometric reasoning. Yeah. Okay, yeah, you can do that. Yeah. Oh yeah, oh yeah. Great question. No, not a bad question at all. She asked, why can't we just like get y by itself and put it in y equals mx plus b form ourselves? You can, 100%. What you'll do is you would subtract, 8x from both sides here. So you're gonna have -2y equals -8x minus 8. divide both sides by -2. You got to divide everything by it. You'll end up with y by itself. -8 divided by -2 is +4. -8 divided by -2 is also +4. You'd end up with the line y equals 4x plus 4. You'd have a y-intercept of 0, 4, which you could graph here. And then instead of using the x-intercept, which you no longer care about as much, you can use the rise over run interpretation of slope. And you can say, my slope here is 4, aka 4 over 1. So if I go 1 unit to the right, this thing needs to go up because it's positive, 1, 2, 3, 4 units. And that's how you could get 2 points. You wouldn't use the x-intercept there. You would use these 2 points. Does that make sense? You can 100%, yeah, you can 100% do that. In fact, for me, if you're on, an exam for me, graph in the way that makes sense to you. If it makes sense to you to put it in y equals mx plus b form, by all means. In fact, that's normally how I would graph anyways. I don't really bother with doing the intercepts, but it's a nice, easy way to do it. But it's really only easy if you happen to have your line in this form, where the x, then the y, and it equals some number. If you don't have that, or if it turns out your x and y intercept are both the origin point here in the very center, then you can't use that one. Oops. So now let's try graphing one. So that's one way you could do it. Let's do it more interesting. Now we can start graphing by using the slope and y-intercept. This is a good problem to work. We can find the slope of the line that crosses through these 2 points, 7, -3 and 9, -1. Our slope is basically the difference between the y values divided by the difference between the x values. So our 2 points are 7, -3 and 9, -1. x1, y1 we'll call them. We'll say this is the first point, so its x-coordinate is x1, its y-coordinate is y1. This is the second point, so its coordinate is x2 and y2. And as long as you're consistent, y2 minus y1, oh, I'm doing -1 minus -3. Divided by x2 minus x1, so 9 minus 7. And it's always subtraction. So if you end up subtracting a negative, that's okay. Just remember that turns into addition. That becomes -1 plus 3 over 9 minus 7 is 2. And this becomes a very simple one, 2 over 2. 2 divided by 2 will give you what? 1. So our slope is just 1. That's like the most simple slope you can get. Just happens to be the case here. And what that means is the slope is 1 over 1. So every 1 unit I go to the right, does this thing go up or down 1 unit? Up, exactly, because it's +1 slope. So these are all some good problems to work. Let's see if we can find an interesting one. No, this one's interesting. Fortunately, I have to zoom out differently now so I can see everything. Yeah. So now our equation, it's already written in the preferred form, which is the y equals mx plus b form. Oh, you gotta love that y equals mx plus b form because that gives you so much information about the graph. We're gonna have a slope m of 5 over 6. It's the number in front of x. That's the slope. The y-intercept, the yint, You're tempted to just say it's 3, and you're not horribly wrong or anything. Just remember it's got to be the coordinate 0, 3. Always a 0 the x-coordinate has when you're talking about the y-intercept. The slope is positive, so that means this line as I go from left to right is going uphill. And it's 5/6, which means every 6 units to the right, go 5 units up. Because it's rise over run. So we will graph our line, and actually I'll use their grapher. Here's their line tool. The y-intercept is 0, 3, so we come over here and boom, there's 0, 3. And now every 1, 2, 3, 4, 5, 6 units I go to the right. I go 1, 2, 3, 4, 5 units up. And there you go. You've got yourself a line there, Pilgrim. And we did this using the slope and y-intercept. You would always think about it as going from left to right, because it's like reading a book. You always read from left to right, which is interesting. In other countries, some of them will read from right to left. They do that in Israel. But anyways, you always go left to right, and then you pick up or down based on whether the slope is positive or negative. So if this, let's tweak it slightly. If this was negative 5/6 x plus 3, we're still going to go from left to right. But for every 6 units I go to the right, how many units am I going to go up or down? Now you're going down. My y-intercept is still going to be 0, 3. So now when I'm graphing this thing, let's just redo it. I start at 0, 3. And now every 1, 2, 3, 4, 5, 6 units I go to the right, now I go 5 units down. The reason that you don't want to go left and down is that those two would be kind of undoing each other's effects, and you'd end up with a positively sloped line, which is not what you want. Because it's like, if I go forward and up, that's the same as, kind of in a weird way, as the line going back and to the left. It's like they're undoing each other. It's like they're canceling each other out if I do that. So I got to hold one of them the same. I got to go to the right no matter what. And then the other one I can switch to up or down. Put a better way, you were saying, well, what if it was negative? Should we go 6 units to the left, like here, and then go down in that case? But if you do that, suddenly you have a positively sloped line. So it's like you're undoing the effects of it. So it's better to just think about, oh, I have a negative slope, so it's going to be on a downward trajectory like that. That's always the best way to think about it, I think. Okay. So what we have now, we have a completely different thing here. We have an inequality. When you have an inequality, you're not only going to be graphing a line, you're also going to be shading a region of the graph, either above or below the line. So here we have 5x minus y greater than or equal to 10. First, we got to graph the line. So we're going to pretend that we have the equation 5x minus y equals positive 10. We're going to pretend like we have an equation just for a hot minute. Now, here you can graph using the intercepts or move the 5x over. I like this idea. Subtract the 5x from both sides. Multiply both sides by -1 so that you can get y by itself. That's going to flip the sign on everything. So y equals 5x minus 10 is what this line is. So first, graph that bad boy. Grab your line tool. The y-intercept is 0, -10. So that's this point. Now the slope is +5. You can think of that as 5/1. So for every 1 unit I go to the right, where do I go? Up or down 5 units? Up. Now that would be the line itself. Now, do we make that, let's select the line, a dashed line or a nice good old-fashioned solid line? It's solid because we have a greater than or equal to. Whenever you have the or equal to thrown onto it, it's a solid line. If you had a strict greater than, this would be a dashed line. So we've taken care of the first part, really the hard part. We have to graph the line itself that's being represented. Now we have to do some shading. We either shade above the line in this region or we shade below the line in this region. What we need to do is we need to pick a test point. The only rule for the test point, it can't be a point that's on the line itself. So I can't use 0, -10 there because that's a point on the line. But then I could use any other point outside of the line. What is the easiest point to use? 0, 0, absolutely. I'm going to use this as my test point. The only time I can't use it is if the line happens to cross through that point, but it doesn't here. So my test point is 0, 0. It doesn't matter. I'm going to plug a 0 in for X and a 0 in for Y. It doesn't matter if I get a true or false statement, that's still going to tell me which region to shade. So the test point, I'm plugging in a 0 for X, because that's the X coordinate of the test point. I'm plugging in a 0 for Y. And I'm asking, is this a true statement? And it won't be. 5 times 0 is 0. You're going to get a 0 on the left, all told. And you're asking, is 0 greater than or equal to 10? Is that true? No, 0 is definitely not greater than or equal to 10. We get a false statement. That's okay. That doesn't matter. All that's going to do is tell us this is not the region that should be shaded. The region that had my test point in it, because it gave me a false answer, that means I don't shade this region. I shade the other one. And I can use that little paint bucket in here. When you're working this out by hand and paper, you're just going to have to physically shade. You're going to be provided with a graph, meaning just the XY coordinate plane and all that. It's going to be provided for you. And then you just have to shade the appropriate region of the graph and draw the line. If you have to dash it by hand, just draw the line, use a straight edge, and then just erase. Or if you don't have a straight edge and using a pen, something like that, just try to freehand dash draw it, and I'll kind of get what you're going for. Does that make sense? This will make sense? So the determinations you need to make, you got to graph the line, then you got to decide whether it should be a solid line or a dashed line based on whether or not you have a or equal to. If there's an or equal to, it's a solid line. If it's strictly greater than or strictly less than, it's a dashed line. Then you use a test point to figure out which region of the graph to shade. Good stuff. We want to simplify the following square root of 50. Here's why we want to simplify the square root. The smaller we can make numbers in general and everything's still the same, that's usually going to be for the better. So technically what we're doing when we're simplifying square roots like this, we are trying to find the largest perfect square number that can be divided out of that. And then we can take it out. So here's technically what we're doing. A little birdie told me that 50 inside the square root can be written as 25 times 2. Right? 50 is 25 times 2. How did I know that 25 would be a fortuitous number here? A little bit of experience and wisdom. And I'm going to show you the way you can do it that way, or the way you can do it that's more general. According to certain rules of square roots, I'm multiplying inside the square root like this. I can separate this into multiplying two separate square roots. Square root of 25 multiplied to square root of 2. Why can we do that? Because of, we call it it's technically because of the product rule of exponents, but we have not learned yet that square roots are just taking an exponent of sort. And I did that simply because I knew 25 was a perfect square. What's the square root of 25? 5. So this just becomes 5 times the square root of 2, which is sometimes you don't even write the times. You just call that 5 square roots of 2. That's how you literally say that out loud in English. 5 square roots of 2. So isn't this a little bit better to deal with than square root of 50? It looks a little more handsome. Does that mean that it's actually simpler? Not really. And actually, knowing that it's really supposed to be square root of 50, you know that 50 is in between 49 and 64. Thus, the square root of 50 is between 7 and 8. Looking at 5 square roots of 2, I probably wouldn't be able to tell you that's a number between 7 and 8. It looks prettier, but to me, it's a little less intuitive. But c'est la vie. Everyone say la vie, please. Everyone say that out loud. No, I'm kidding. That's a really lame joke. It's a really lame joke. So that is the kind of, if you can see it kind of way. And hopefully as you're working these, you'll get better and better and you go, oh yeah, I see that. Now in this case, if you can't automatically see it, that's totally fine. There's an alternate way of simplifying these square roots. Take your 50 and find its prime factorization. What are two numbers that multiply to 50? 5 and 10. 5 is as good as it gets, the Jack Nicholson movie. 10 can be broken down more. What does 10 become? 2 and 5. I'll write the 5 first so that we can see a connection. So the prime factorization of 50 is 5 times 5 times 2. And I'll write that just for kicks. You can write it like that. Now, once you have the prime factorization and we know we're simplifying square roots, you circle any pairs of factors. In this case, 5 is paired up with another 5. Anything you circle, you're going to bring it outside of the square root, but you only need one representation of it. Because what you're secretly doing is you're taking the square root of 5 times 5, which knocks one of those 5s out. This, though, did not get to come out of the square root because it didn't get paired up with anything, so it's left inside the square root. And so we end up with 5 square roots of 2. Bada bing, bada boom. Let's work another one. I think these are good ones to do together. Yeah, that one's not so interesting. This is a good one. 5 square roots of 45. There's already a 5 out in front of there. That's okay. Don't let it bother you. We're going to work this one both ways. Both the intuitive way and then the way that's using prime factorization, which may still be intuitive for you. It just depends. This is just 5 times the square root of 45. So here's what we're going to do. We're going to get our ducks in a row with the square root of 45 by itself almost. And then whatever it ends up being, just multiply it by that 5 that was already there. So don't let the inclusion of that extra 5 throw you off. Now, just by seeing it, what is the largest number you can divide out of 45 that is itself a perfect square? I think it's 9. Yeah, I don't think you can go any bigger than that. So what we're going to do is we're going to rewrite this 5 times inside the square root. I'm going to call that 9 times what? 5, exactly. And yeah, so in other words, you're looking for the largest factor. the largest multiplied factor that can be branched off. Because now, again, that 5 is in front there. It's only coincidental that this is a 5 and this is a 5. There's no magic behind that. Now I'm going to branch off the square root business into square root of 9 and square root of 5. Now I could have taken 45 and called it 15 times 3, but that does me no good because 15 is not a perfect square and 3 is not a perfect square. 9, though, is a perfect square. So what's the square root of 9? 3. So this becomes 5 times 3 times the square root of 5. And then we can just do that 5 times 3, which will give you what? 15, and we still have the square root of 5 there. So that becomes 15 square roots of 5. Does anyone want me to work that the prime factorization way? Does this way make sense? Now, I will tell you the prime factorization way is going to be appropriate if you had a really large number. If you had like, if you had like a square root of 3681, 3681, good luck. You probably aren't going to be able to figure out the largest perfect square that can be factored out of that. So in that case, using the prime factorization method may be appropriate. But if the numbers aren't horrible, then it won't be horrible. Let's see if there's one more. Yes, these are good ones to work. How about this guy? 2 square roots of 8 plus 3 square roots of 18. Oh no, we'd love to add those together. You can combine square root expressions like this if the number inside the square root were the same in both cases. But is that going to be it here? No. So maybe we can try our cute little way of simplifying square roots and see if by applying that we end up with like terms, so to speak. So let's zoom in on the square root of 8. There's already a 2 in front of it, but that shouldn't scare you. What is the largest number that can be divided out of 8 that's a perfect square? 4, exactly. So this could become 2. The square root of 18 can be written as 4 times 2 on the inside of the square root there. Plus, what's the largest perfect square that can be divided out of 18? 9, yeah. And there's a 9 times 2 left in there. Now we're going to split them up. Because now what's the square root of 4 going to be? So it's going to be that 2 that was already there times now the square root of 4 times the square root of 2 plus that 3 that was already there. What does the square root of 9 become? Also 3, and there's still just a square root of 2 left. Now we just multiply these. What's 2 times 2? 4 square roots of 2 plus what's 3 times 3? 9 square roots of 2. Now we get to this stage, and the cool thing is we could combine these, couldn't we? Imagine if you had 4x plus 9x. You could combine those into 13x, couldn't you? It's the same idea here, only instead of an x, you're talking about the square root of 2 being your object. You have 4 water bottles, you add 9 water bottles. You're adding the 2 categories that are the same and just different amounts of them. So what will this turn into? Not a 4, just 2. Yeah, we're just saying that we have 4 of this object and adding 9 more to it, but it doesn't change the nature of the object itself. And so that's how we could simplify it. So 2 square roots of 8 plus 3 square roots of 18 is kind of nasty, but it's exactly the same as 13 square roots of 2, which is a little less nasty, isn't it? It's a lot more manageable. Any other questions? Is there anything else you guys want me to review? Our finals tomorrow morning at what time? Just our meeting time, 9 o'clock. We're meeting in person, right? Yeah. Both days, tomorrow and Wednesday, we're meeting in person. So don't forget that.
I'm going to be allowed our own scratch paper, or are you going to provide that?
That's a great question. There's the exam's going to be on paper, and you're going to have plenty of space to work problems out in there. So you're not supposed to use scratch work because I need to see your work.
Okay.
And you'll just try to do your work on the problem. But if you do want some extra pages just to like try something out, you can do that. That's fine. You can have extra pages, and then just make sure you transcribe the correct work or your final work onto the actual problem.
Okay.
So good question.